Okay, for this refrigeration cycle, the idea is to use a training unit to understand the concepts behind refrigeration. And for that, we have a particular unit that's called Model 9001 Basic Refrigeration Training Unit. So it is instrumented, and it is not really what you see in commercial applications, but it is made for this particular lab. So what I'm going to do is I'm going to describe to you the basics of the unit and then how you're going to do the measurements in here. So the unit has 4 different main components. 2 components are basically heat exchangers. One is called the evaporator up here, and the other one is called the condenser down here. And these evaporator condensers, their job is actually to change the state of the fluid from either liquid to vapor or from vapor to liquid. So they kind of store the heat in that way or release it. And then in addition to that, we have 2 other components, very important. One is to raise the pressure, which is the compressor right here. And the other one is to reduce the pressure. And to reduce the pressure, we have an orifice. And the orifice is one of these 3. So these are 3 orifices in parallel. And each one of them has a particular function, and it is used in a number of applications outside our system here. So in addition to having pressure reducer, pressure increase device, 2 heat exchangers right here, then we have to look at controlling the flow in the system. We have Freon. As you know, we have Freon is R12, and the R12, it's in a liquid phase some of the time, and then it will be in a vapor phase some of the time. So I'm going to go over the system. As you know, the cycle is typically has 4 points, 2 points at low pressure, 2 points at high pressure. So what I will do is I'm going to follow the cycle on a practical sense, which is right here on this unit. So let's look at the cycle. We're going to start from this device. This is a passive device. It's called receiver, and it's basically a container, and its job is to receive the liquid that comes from the bottom of the condenser. So the condenser has condensed liquid, and the liquid goes into the receiver. And the receiver allows for some time for equilibration, so we don't have any entrained vapor coming out of the receiver. So the receiver, at the exit of the receiver, this pipe here, we know for sure that we have saturated liquid conditions and there's no vapor whatsoever. And to check on that, we have an indicator that gives us by color, just if we have color, green color, then we have liquid, that we know the state of the fluid here, that it is on the saturation dome, as you'll see in my lecture. So this fluid is going through a measurement device here, which is a flow meter, and the flow meter is similar to a rotometer, in which we have a bob, and the bob will float, and the flotation of the bob is a balance between the gravity and the forces of buoyancy and the forces of drag. And it is calibrated here only to measure in pounds per minute for R12. So if you look closely here on the sign, you see this is ppm for R12. So if it is, let's say, the top of the bob is situated at 1, this means that you have 1 pounds per minute of R12. Now, in order for us to measure the R12, the Freon has to flow through the flow meter, which means that this particular valve has to be closed. So if you look at it, closed will be right here. So if it is closed, it means that we get the Freon flowing through the flow meter, which allows us to measure it. However, for some settings, we must use this valve in an open position, so we will be able to open it. And when we open the valve, then the flow is diverted from the flow meter and goes bypassed to under this pressure gauge in here. And I'll explain to you the conditions for that. Conditions for opening this is basically when we see that we have very high velocity fluid entraining bubbles, and we are worried that the bob will actually block the flow meter, and that would increase the overall pressure in the system and trip it. So we have to be careful with that. Okay, so now we have saturated liquid, and we have a pressure gauge, and the pressure gauge measures pressures at P1. This is 0.1, and the gauge is graduated from 0 all the way to 500 psi. And you have to know that this is PSI gauge. It's not PSI absolute. So in the analysis, we have to add the atmospheric pressure, which is 14.7 PSI, to that to make it into absolute. So now this will be highly pressurized fluid, and it's all liquid. And the liquid is now going through, and it will now have to decide to select one of these 3 expansion valves. So if we have the expansion valve, the first one is a capillary tube. If it is closed, then the fluid cannot go through it. And the last one is a TXV, which is thermally controlled. If it is closed also, the fluid cannot go through it. So the first set of experiments, we have to open that valve. This is the pressure controlled valve. And that valve provides an orifice inside right there. And this orifice, the cross-sectional area of the orifice can be controlled by the action of a spring. And we can control the cross-sectional area by using this screwdriver, which has a hex head. And then if we tighten it, this means that the cross-sectional area is reduced. If we and the pressure will be higher. If we loosen it, then the cross-sectional area is increased and the pressure gets lower. So in the first set of experiments, this is what you'll be controlling, the cross-sectional area here, so that you can control the inlet pressure to the compressor, as we will talk about it in a minute. But going back to here, the fluid is going through the orifice, and is going through the orifice. It will expand, and once it expands, then the liquid phase will partially change to a vapor phase. So we have a 2-phase flow coming out, and the temperature correspondingly is reduced. So you will see a lot of frost when we turn on the system right here because of the reduction in the temperature following the expansion. And you will see that the pressure P2 is significantly lower than the pressure P1 because of this kind of pressure drop. Now we have 2-phase flow, and the top viewing tube, which has plexiglass to allow us to view what's going on here. You will see that you have liquid in the bottom and vapor flowing on the top. So that tells you that you have a certain fraction of the fluid in the vapor phase. That's the quality of that system X that we calculate in our lectures, and it's about 20 to 30% in that range. So we have now the fluid is going to go as a 2-phase, and you can see that this is a typical, very efficient heat exchanger, and you have cross flow in internal pipes, and then you have fins, and the fins here have a very large surface area. And if you go to the back side of this, you'll see a fan, and the fan is blowing room air across from here. So the room air will be coming from here, you will see, and the room air is essentially warm to start with, but it will actually lose its energy to the fluid, and when it comes out here, it will be cool. So the cooling effect is going to be felt on the top here. And to measure the temperature of that cold air, we have temperature sensors right there, and we'll talk about that in a minute, but these sensors are connected to a digital thermometer. So now we, at the bottom, when you will look the bottom here, you'll see total vapor or complete vapor, maybe close to 100%, and the vapor is flowing down here, and it is at lower pressure. So if you look at the vapor, will be coming down. And by the way, now since I'm at this point here, there is a temperature sensor right there strapped to the main flow. Because of the high conductivity, the temperature of this main flow is the same as the temperature in the enclosure here, which also contains Freon, and the Freon is fed to control the valve opening in the thermally controlled expander right here. So the thermally controlled expander opening is dictated by the temperature of that point, and as we'll discuss in a few minutes. So now the vapor is coming down. This is closed. It cannot go. So it has to go through the open valve. And this you cannot touch because everything is taken out, so you don't have to play with that. The flow is just regulated to go through here. This closed, it goes through here. Closed, it goes down. And finally, it goes to a passive device called the accumulator. And the accumulator has the same function as the receiver. It's just passive. It accumulates any additional liquid droplets that we would like to prevent from going into the compressor. So out of the accumulator comes vapor, and now we know that we have dry vapor because it's very important to have dry vapor going into the compressor. So the compressor here is dry vapor. And the reason is that compressors work very efficiently on dry vapor because we have compressible fluid, so they can affect that. And also in addition, if we have any liquid droplets entrained in the vapor, they will impinge on the vanes of the compressor and cause thermal damage and thermal fatigue. So that's why we have the accumulator. Now going back to the compressor, at this point, P3, you'll see this is the lowest pressure in the whole system during the cycle. So P3 will be quite low, and in fact, the first set of experiments that you'll do, you'll control P3 itself to remain around 2 psi and perform the experiment, and then you will control it again to become 7 psi, and then you perform the experiment, and so on. The way that you will control the value of P3 is going to be by tightening or opening the valve here for the first set of experiments. This is the pressure-controlled valve setting. So going back to the compressor, we have now low pressure. Compressor is going to perform work, mechanical work on the fluid. And in the process, two things will happen. First thing is that the surface of this compressor is going to be very hot because there's a lot of mechanical work, and you have to be very careful, safety-wise, not to touch that compressor because the temperature can be about 250 to 300 degrees Fahrenheit. And the second thing is that the pressure is going to increase dramatically from the low value that you set yourself. You set this to be 2 or 7 or 15. This is the value that is dictated by the experiment, to a high value, which is here. And that would be on the order of 120 or so, 120, 130 psi gauge. So that's the compressor. It has a function. If it were insulated completely, then all of the work that it's doing, it would have gone to the fluid, and it would have been extremely efficient. However, most of the inefficiency would be coming from the fact that this compressor is losing heat, and this is what we're going to go through in our lecture. So coming back to the compressor, this is compressed vapor, and the vapor is very, very dry here, very high pressure, very agitated, so it's going to want to condense. So to condense, we take it to a condenser. If you look at this glass indicator, you'll see that it's very dry vapor, and because it is very hot, if we blow room air from the back, which we do, then we have heat exchange process. The fluid is going to lose its heat to the incoming air from the back. So out here, the air is going to be warm, and the compressor is going, the condenser is going to let the fluid condense, and down here comes liquid again, and then we can repeat the cycle. So this is just the whole cycle now.